Okay, so this is video 2, if you're just making sure you're in the right order, where we're still discussing this antiderivative, again, integral, antiderivative, two terms that are going to be used interchangeably. So I use this, the last one was really largely conceptual, where I was trying to show you what it is, kind of where that problem comes from. So we're going to sort of jump into it now. The first couple examples I'm going to use are, I'm working my way to a point. So by the end of hopefully this video, I'm watching my time again, but by the end of this video, when I really start to kind of crank through some practice problems, that's where the process of what I'm doing will hopefully make more sense. And I picked pretty easy, straightforward problems for your homework to just build your confidence. So it will, I think, continue to feel as abstract as you are watching these notes until about the end. Okay, so an antiderivative, the formal definition of an antiderivative, and I use the notation from your textbook here, is a function, capital F, is an antiderivative of lowercase f on an interval I if the derivative of the capital F function is equal to the little f function. Okay, so I don't know. I'm all about formal math definitions. They're very good to have, but when I look at that, especially for my first time around, I would be a little bit confused. So I want to use a tangible example, and this will also present a new thing that we need to get into our antiderivative work, and that is the constant. So if I have 3 functions, I'm going to use the ones that are in your textbook, and I'll use this capital F notation. So function 1 is going to be x cubed. Function 2 is going to, of x, sorry, is going to be x cubed minus 5. And function 3 is going to be equal to x cubed plus 97. Okay. Now, what I would say, the textbook says it, of course, is that all 3 of these functions are antiderivatives of a single function. So the function f of x is equal to 3x squared. And so let's look at why. All 3 of these functions, if I take the derivative of this first function, the derivative of x cubed is 3x squared. If I go to the second function, the derivative of x cubed minus 5 is 3x squared, right? The derivative of x cubed plus 97 is 3x squared. So what we see here is that I could have listed 1,000, there's a really infinite number of functions I could list here to get a derivative of 3x squared. The point is that all the functions have to have this value, x cubed, and then I can add or subtract any constant from that, right? Because the derivative of that constant term is 0. So these are all antiderivatives of this function. So if I am trying, so this is like if I'm given this function, this is like I'm given the derivative, and I would have to find my original function. So the original function, which is the capital F, is an antiderivative if you take the derivative of this function to get back to this, okay? So I'm going to integrate what I'm given, or I take the antiderivative of what I'm given to get any number of possibilities. We'll talk about how we could note this. And I can check myself by taking the derivative of my answer, and I hopefully get back to what I was given. So it's working backwards. Okay, so if I'm given the function 3x squared, and I'm asked to find, and we'll go through how, but if I'm asked to find the antiderivative of this function, clearly, as I keep saying, there's many possibilities. A way to generalize this is that the antiderivative, so capital F is how I'm noting my antiderivative, is equal to x cubed plus c. where c is any constant, right? Because the derivative of the constant is 0. So it could be a negative value like -5, could be a positive value like 97, could be 0. There's not a constant here. Could be anything else in between. So this is how we would write our answer. So if I were given this original function, 3x squared, and I'm asked to find the antiderivative or the integral of this function, my answer would be x cubed plus a constant. And again, if I want to check myself, and let's say I'm not feeling confident about this answer, I want to check myself. Okay, x cubed, what's the derivative of x cubed? 3x squared. And so we know we're in great shape. Okay, so it's kind of the idea. So we have a couple of terms coming out of here. And so if I'm going to write it as, sorry, I think I skipped a slide, but I'm going to do this and then I'll work back to the one I skipped. This is my notation for antiderivatives or integrals. This is what I was thinking about doing earlier in the last video. Okay, so this is the notation we see for antiderivatives or integrals, and I just want to kind of put the terms that you would see used for this. This is called the integrand. This is the function that you are integrating or finding the antiderivative of. So this 3x squared, for the example I just did, would be my integrand. dx, so this comes from that Leibniz, I say Leibniz, from the Leibniz notation, so it's a little bit different notation than what you've been used to seeing Newtonian. But the formal term for this is it's the variable of integration. This just tells us, so it comes from writing differential equations, which I sort of skipped and glossed over because I was told that's more of an AP concept. So for us, I'm sort of waving my hands at it, but it is the it's the variable with respect with, oh my gosh, I can't speak. It's the variable which we are going to integrate with respect to. Okay, so if I had some function here, i.e. 3x squared, I'm going to integrate that with respect to the function x. I might have other variables. I might integrate with respect to t, like if you had a function for t that I was doing with my velocity and my positions in the previous video. Well, then this, instead of saying dx, could say dt. When you do more spherical geometry things, we're really not doing a lot with that, but it could be r. So for us, almost always it's going to be x, but this is just the variable you're going to integrate with respect to, so you don't really do anything with that. Then when we get to our answer, so f of x, this is the antiderivative. So it's like my answer. And this c is what we call our constant of integration. And hopefully it makes sense why we have to have that in there. It comes again from this idea, right? Because the derivative of the constants are 0, it could be any constant. So another way, if you want to picture it, I don't know if this helps you or not, but I'm go to my graphing thing because I'm a more visual person. I can have on a graph, this is kind of sloppy and I know it's hard to see, I can have any number of parallel lines or parallel curves, if we want to make it a curve. And all of these lines, or curves, they're all going to have the same slope, right? So they're going to have the same derivative, but they might have these different values in, right, just based on their position. So that's the idea. Okay, so we're going to do a couple of practice problems. The first one may seem strange. I don't know, maybe not. Okay, So the first one has this term, this other term that I haven't really discussed, and that term is differential equation. So the first problem says, find the general solution of the differential equation y primed is equal to 2. So differential equation is just an equation, usually with x's and y's, it could be other variables, but it's an equation that involves whatever your variables are going to be. Let's say x's and y's, so we'll do this as an x and a y. So it's an equation that's going to involve your x and your y's, and it's going to have a derivative in it. So this equation, I'm saying the derivative of y is equal to 2. So it's simply a differential equation because it has a differential, which is a derivative, in it. So here's an equation with a derivative in it. We call it a differential equation. So I want to find the general solution of the differential equation. So when they're saying find the general solution of the differential equation, they're asking you to, it's just a mathy way of saying integrate or find the antiderivative of this. So if I know that the derivative of a function is 2, what I want to do is find that original function. That's what it's asking me to do. So what's the original function? What has a derivative of 2? So if I think about this, 2x has a derivative of 2, right? That's the only thing I can think of that's derivative is 2. If I'm keeping that x and y. Of course, this could be any variable, but let's keep the x and y. So y is equal to 2x has a derivative of 2. But, so I want to find the general solution. They don't give me any, the general solution meaning they don't give me any real specifications here. But I could add or subtract any constant term from this 2x and still have a derivative of 2. So the actual answer would be y is equal to 2x plus c. So I have taken or found the antiderivative by integrating this function, okay? All right, so in your textbook on page 250, and I will also scan in and send you a handout for this. There is a great table with all the rules for integration. And when you're integrating or finding antiderivatives, you're essentially doing your rules for taking derivatives and working them backwards. The one we are going to work with the most at first is the power rule. So that one I want to specifically run through, and then we'll do some practice problems. Okay, so if you have the function I had before, 3x squared. And I already said when I take the integral, so when I find the antiderivative of this is equal to x cubed plus any constant. So the question is, how did we get to x cubed? So you know to take the derivative and use the power rule, you multiply out by the power, right? So you're going to take your power and multiply it out, so you have 3x, and then you subtract 1 from the power, right? So the derivative of x cubed is 3x, and then I subtracted 1 from the power. That's how you use the power rule to find a derivative. When you use the power rule for integrals, you do the opposite thing. So if I want to integrate 3x squared, I'm going to use the power rule like in the opposite way. So I add, and this is all in that table, but I'm just going to run through it. I add a power. So instead of 2, I will write 3, and then I divide by my new power. And so I'm left with x cubed. So we would say the integral or antiderivative of 3x squared is equal to x cubed. I've gotten back to my original function. So if given this one, I can work, if given the derivative, I can work my way back to the original function. So again, what I did here is I don't mess with the 3 because it's just a constant. I look at my x squared. I add a power to make it x cubed, and I divide by that new power. Again, the rule for that is in the table in your textbook, and in the table I'll send you, but that's the one you're going to see me using most often as we do these practice problems. Okay, so when you are doing integration problems, there's essentially 4 simple steps, and I will start by showing every single step of these 4 steps, but there's 4 simple steps that you follow. 1, you write the original integral, which is like what the problem will give you. 2, you rewrite it, and you'll see why in a minute. 3, you integrate it. 4, you simplify it. And you'll see in the textbook, and so I'll do this too, when we're doing the practice problems, it's nice to actually make a table out of this. So actually they'll make columns like original equation, rewritten equation, integrated equation, simplified equation. And that's a nice approach to taking with problem solving. Now I'm watching the time, and I'm at 16 minutes on this video, so I'm going to come back for a 3rd video and solve the problems. And we'll crank through them, and actually, ironically, the problem solving one will probably be the quickest of them all. And then you can start your homework, okay?